Hello, everyone. This is Dr. Young, and in our third part of our discussion of quantum numbers and orbitals, we're going to talk about that magnetic quantum number, m sub L. This will describe to us kind of how many orbitals are in the subshell, like the s subshell or the p subshell, and also the orientation of those orbitals. How do those electron orbitals look different? So we are talking about this. Here we are, quantum numbers. We're talking about m sub L. We already talked about n. We already talked about L. So now we're talking about m sub L, and that's just an m with a little subscript that is that fancy curly L. Here's that table again. I kind of modified it to clarify some of the language from before. N is a principal number, right? Determines the size and the energy of the overall shell. Angular momentum is talking about the subshells. So are you talking about the S subshell, the P subshell, the D subshell, the F subshell, etc. We now are going to talk about the magnetic quantum number, which is going to give the orientation of the orbitals and how many orbitals are in each subshell. So the fact that when you're talking about S's, you only have one. When you have an S, you only have one orbital. When you talk about P's, you have 3s, D's have 5, F's have 7. And then we'll talk about the spin number, quantum spin number later. So the magnetic quantum number m sub L is going to answer the question for us: how many orbitals are in each subshell, and what's the orientation of the orbital? The allowable values that we have are basically that your m sub L values are going to go from negative L through 0 to positive L. So for example, if you're talking about when L equals 0 here, all right, so L equals 0, we're talking about the S's. If your L equals 0, then the only m sub L value that you can have is 0, since negative 0 and positive 0 is the same as 0. There's only 1 here, so this is only one orbital. If you're talking about when L equals 1, which remember is your p orbital, then your L's can be from negative 1, right? If your L is 1, your m sub L's can be negative 1, 0, and 1. Or in other words, there are 3 orbitals. When you're talking about your D subshell, right, when your L equals 2, your m sub L's can be from negative 2 to negative 1 to 0 to 1 to 2 for a total of 5 orbitals in that D subshell. And then lastly, if you're talking about your F's, your L equals 3, then your m sub L can go from negative 3, negative 2, negative 1, 0, 1, 2, 3 for a total of 7 orbitals. And this is going to be always true for all F's, right? All F's have 7 orbitals, all D's have 5, all P's have 3, and all S's have 1s. And I put these diagrams right here, right? So here's a 1s. Principal number is 1, because you got the big fat 1 there. S, that means your L is 0, but there's only one 1s. It's just this little spherical thing. You jump to 2s, it's the same thing. It's still spherical. It's at a higher energy level now. It's a bigger orbital. But there's just one of that type. There's only one 2s, right? There's only one m sub L. And let me put that in the same colors, right? The m sub L for this is 0. The m sub L for this is also 0, right? That's the value of it. There's only one of them. But if you go to a p orbital, right? Remember that p orbitals, we said, kind of had this like dumbbell shape, right? Or again, sometimes drawn as like 2 spheres over another one. The idea is that it's a dumbbell, and in the center of that dumbbell, I'll draw it in black this time. The center of the dumbbell, that's the nucleus. And in fact, I want to draw this a little bit cleaner. Right, here's the nucleus, and then we have the p orbital, right? That's what a p orbital would look like. But now, given that this is a 3-dimensional world, the idea is that we have a 3-dimensional axis, right? So in this particular drawing, they're calling this the x, the vertical is the x-axis. They're calling the y the one coming out at us and going away from us. And they're calling the z the one that's going from left to right. So this is supposed to be 3-dimensional, again, where the y-axis is coming right out at you. This point's coming right into your face. That part's going right into your computer screen. And so the idea is that this p orbital can be lined up in any one of those 3 ways, right? This is the orientation of the orbital. I could have the orbital line up like this, and that would be the px, which is drawn here, right? This is the px. This would be one of those values, right? This would be like saying you have an m sub L of equal to negative 1. Or you could have, for example, the orbital line up like this. It's hard for me to draw this 3D, but this would be along the y, where it's coming out at you. That's what this is supposed to be, where it's coming out the y. And you might call this an m sub l value of equal to 0, right? That'd be the other one, right? Because we have, again, -1, 0. And the last one's going to be 1. This would also be an m sub l equal to 1, where you had that last orbital, and I'll draw a new xyz coordinate here. And then you'd have a last one where you lined up your p orbital along the z, right? So x, y, z. And that'd correspond to a third direction in which you could have this orbital align, right? So for p orbitals, they have the three main directions, right? X, y, and z, ways that you can orient them, either straight up and down, coming right out at you. See, there's a little red, the red lobe is poking up behind you, and or left to right, right? Or left to right. And again, so that's why we got these 1, 2, 3 m sub l values, -1, 0, 1. Now, does -1 always correspond to x, and does 0 always correspond to y? No, they're not consistent. You should just know that the three different orbitals here, right? These are three unique orbitals. They have those three different values. That's the main thing I want you to get out of that. It's not always that the pz is 1, for example. That's not always necessarily true. I do also want to mention, while I have this drawn, is that, again, you see that there are different colors here. Different colors, different shading. And what that corresponds to is different wave signs, different signs. And that's not going to be super important to us right now, but it is an important feature that I want you to know. So different signs. And by signs, I mean, right, remember that for waves, you can either have a wave start off going up and then down and then up and then down, or you can have a wave start off going down and then up and then down and then up. And so these would be considered different signs, right? You start off going up, that's one sign. You start off going down, that's the opposite sign. So what we're saying is that these represent opposite wave signs. Sometimes these are given positive and negative connotations, which is, I think, confusing because that implies charge. That's not what this is at all. Our book, I don't even think has different colors. They're all one color. So that's really annoying to me. They should be different colors. S's, they all have one lobe. They're all the same color, whether it's blue or red. It's irrelevant. But P's have two different lobes, and they are different colors. And we'll see in the next slide that D's have different lobes, they have different colors, etc. So I want you to just pay attention to the fact that these have different phases, different signs, and I'll put comma, different phases. Right, again, where the phases is your wave starting going up, or is your wave starting going down? Those would be different phases. They're equivalent, but opposite. Now, if you take a look at this that I showed you before, right, remember that we said that this was the S's. And so you have an S here that just has its m sub l that's equal to 0. If you look at your next one, right, which we said was the P's, the P subshell, there were three values, and we just talked about this on this one, the -1, the 0, and the 1. Notice that there are different orientations of this p orbital, right? And they, again, have different colors. They have orange and yellow in this one. There are different colors in the previous slide. If you look at the next, right, so when L equals 2, we're talking about d orbitals. There's m sub l's are -2, -1, 0, 1, and 2 are the different types of d orbitals that you can have. These are a little bit weirder. So these have 4 lobes now. Notice that there's 2 different phases, a purple phase and sort of a turquoisey phase. And you can have it flat along the xy plane. You could have it on the xz plane. You can have it on the, let's see, what is this? The xy plane and then something in between. And then there's this weird donutty thing. We're not going to really stress out too much about the shapes of these. We're not talking about bonding yet. But I just want you to point out that these are the D's, and these are the shapes of the orbitals, right? The probabilities, those size squared, the probability maps of where we're going to find an electron with given a certain amount of energy. And mathematically, this is what is spat out by these mysterious equations that we don't know, that you and I don't know. Someone knows them. And then lastly, for L equals 3, right, these are the f orbitals. And so when L equals 3, your m sub l's could go from negative 3 to positive 3, which is what they're showing here. Negative 3, negative 2, negative 1, 0, 1, 2, 3. And that's why the f has, right, 7 subshells. It's got it's got 7 orbitals. 1, 2, 3, 4, 5, 6, 7. It's why the d subshell has 5, right? 1, 2, 3, 4, 5. It's why the p always has 3, 1, 2, 3, and why the s only has 1 orbital in any one of its subshells. And again, we're going to flesh out more what this really looks like. Now, what I want to just kind of show you is how we're going to start drawing these energy levels, right? For these s's, for example, that means if I have an s orbital, it just looks like this. That's my s orbital. There's one place for me to put electrons, and that's it. It represents one s orbital. Now, if I want to just represent my p's, right, they have 3 values, so my p's have 3 energies, right, 3 orbitals, but they're all of the same energy, or in other words, they're degenerate. Degenerate orbitals just means that they have the same energy. So I'd say that these 3 orbitals in the p subshell, they're degenerate because they all have the exact same energy. It's not like this one over here, the 1 is higher and the negative 1 is lower. They're supposed to all be of the same energy. Same deal for when you talk about the d orbitals, right? They have 1, 2, 3, 4, 5. So they have 1, 2, 3, 4, 5. Those are my d values. And they're all degenerate also. And lastly, we have the f's, right? The f's go from negative 3 all the way to 3. So they have 1, 2, 3, 4, 5, 6, 7 for your f's. And what we can do is we can put these values, let me give myself a little space for this s. What we can do is we can put these m sub l values below, right? So for s, we know the m sub l value is just 0, so I put a 0 there. For the p's, it goes from negative 1 through 0 to 1. So then I have those 3 m sub l's for the 3 orbitals in the p subshell. If I go to my d's, negative 2, negative 1, 0, 1, 2, right, for all of those values. Same thing for my f, negative 3, negative 2, negative 1, 0, 1, 2, 3. Right, those are all the m sub l values, right, for the f subshell, the d subshell, the p subshell, and the s subshell. And we're going to start using these numbers to help identify where electrons are. All right, because if I have an electron somewhere, like let's say I have an electron here, this is an abbreviation for an electron. We'll come back to that later. This is supposed to be an electron. We'll draw more energy diagrams once we finish the 4 quantum numbers. That little like, it's supposed to be an arrow, but not a 2-headed arrow. It's a single-headed arrow. So I can talk about this arrow right here as having a principal number, whatever this f is, if it's like a 3f or, a 4f or something like that. I can talk about having an L number, which would be 3 because it's an F. And I can talk about having an M sub L, which in this case would be negative 2 because it's in the negative 2 orbital in the F subshell. And again, we're going to get more into this, but I just want to start laying this out so you can start seeing how we're going to put this all together. So yes, S, P, D, F. That's how many subshells are in each, how many orbitals are in each subshell. Now, let's go back to that question where we said, how many orbitals does boron have, right? Remember, boron was right here. It's the first one right here. So if I start reading this, right, remember that when we started, we went through, and let me put up these principal numbers again, the row numbers, 1, 2, 3, 4, 5, etc. Remember that we had the S block, the P block, sorry, the D block right here. P block was over here, and then the F was down here. Remember that our friend helium is actually over here, not there. But if I'm going to describe how I get to boron, it goes through here, right, which is the 1s. And then if it keeps on going, then it goes through here, which is the 2s. And eventually we're going to get all the way to where boron is, but boron is in the 2p, the 2p block, right? It's in the p block and it's in row 2, so it's 2p's. And now when I go to do my energy diagram, like I did before, I know this might seem familiar. Again, I start with my 1s, but now I'm very intentionally only putting 1 dash to represent one orbital for the 1s subshell. If I go up to the next one, same thing. It's still an s, so there's only 1 dash there. There's only 1 orbital in that subshell. What's new for us now is that when I talk about the 2p's, I don't represent the 2p's as 1 dash. I represent them as 3 because there's 3 separate orbitals. There's 3 separate orbitals there. And what you're going to see us start doing, this is a little preview, and I hope this doesn't get too confusing. We're going to talk about in the next video how you can put 2 electrons in each of the subshells. If you look at this, right, boron has 5 electrons. I know that because its atomic number is 5, and we're talking about just a neutral atom, so protons equals electrons. And so boron has 5 electrons, and I start filling these up. I go 1, 2, 3, 4, 5, right? That's the 1. This is supposed to be the 1 electron in that 2p area. There's a 1 electron in that 2p, right? I just barely got into the 2p area. We're going to come back to filling these and why one's up and one's down and why I started at the bottom and everything. But I just want you to start visualizing this, start connecting the number of subshells, the number of orbitals in each subshell to how many electrons we're going to be able to put in. I could, in theory, I don't have this many for boron, but I could, in theory, have put in 1, 2, 3, 4, 5 more into the 2p subshell. More on that later. Let's see if I can just go back there. Goodbye. So let's do the same thing with the silver, right? We said was down here. Here's my silver. And this one was much more complicated. I'm not going to redraw this because we did this in the previous video, but remember that it had the 1s's, then the 2s's, then the 2p's, then the 3s's, then the 3p's, then the 4s's, then the 3d's, the 4p's, the 5s's, and then the 4d's, right? That's how we got all the way through here, right? We had to just read the periodic table left to right. We went through the 1s's, the 2s's, the 2p's, the 3s's, the 3p's, the 4s's, the 3d's, the 4p's, the 3s's, the 5s's, and then the 4d's, right, to get to silver. So that means if I was drawing that atomic orbital diagram, I put in these in order for silver, I'd start down here with just a little 1s, and then a 2s, and then a 2p, and then a 3s, and I'm just reading this, right, same order, but now I'm just adding the fact that I know that my p's have 3 subshells, not just 1, or 3 orbitals, not just 1. After, not 2p's, 3p's. After 3p comes the 4s. After 4s, we had the 3d's. Now the d's, right, their L sub m's went from -2 to 2, so that was 5. So 1, 2, 3, 4, 5 for my 3d's. After 3d came 4p's. After 4p came the 5s. And then my 4d's, 1, 2, 3, 4, 5 for my 4d's, right? Here's the ordering and the number of orbitals that I would have to fill up to get to silver. So this is me combining, right? I've got principal numbers here. I've got the angular momentum number, and I've got the m sub l number shown in this diagram. Again, going from low energy to high energy, right? So the lowest energy is the 1s, the highest energy is the 4d in this case. Now we can answer random questions like this. So like how many orbitals are in a subshell with an n of 3 and an L of 1? Well, I know that they're talking about the 3p, right? Because I've got 3 and the L is 1, so that's a p. And since my L is 1, and I know my m sub L goes from -L through 0 to positive L, that means my m sub L's in this case are -1, 0, and 1. Or in other words, there are 3 orbitals in a subshell. But I am going to start remembering that anyways, right? I know that always when you have a p orbital, there are 3 orbitals in that subshell, that there's 3 in there. So my answer for this would be 3. How many orbitals in this subshell, in the 3p subshell? 3. If I go to the next question, How many orbitals are in a subshell where n equals 4 and L equals 0? 4, so now we're talking about the 4s orbital, right? Because again, 0 is s. And now my m sub L values really can only be 0 because my L value is 0. And so that means there's just one subshell, right? And again, we know that s's only have one orbital, right? They only have one orbital in their subshell. What must the m sub L value or values be for the following subshell? Here's an F. I know that for F, my L equals 3, which means my m sub L values will go from -3, -2, -1, 0, 1, 2, and 3, right? Because again, the m sub L's go from -L to +L. So this would be my answer for this one. Those would be my m sub L values. I'd have 5 for that one. And then lastly, label the m sub L values for the orbitals below. I see here that there's 5 total, which means this must be a d orbital because the L must be 2 and my m sub L values must go from -2 to -1, 0, 1, and 2. Right, since I saw splitting of 5 there, 5 orbitals in the subshell, I knew it was a d. And since I know it was a d, I know the L has a value of 2, right? Because all d's have an L value of 2. So therefore my m sub L's are -2, -1, 0, 1, and 2. So we're real close to finishing out all this quantum number stuff. So for the very last thing, so the next video we're going to talk about is what is this m sub s? What is this quantum spin number? How are we going to use that to help inform what the electronic structure of an atom is, right? What orbitals are being used? How many electrons can fit in those orbitals? And in what order do they fill them? So watch out for the next video. M sub s is what we're going to talk about. Keep studying. Good luck.